Pythagoras was a Greek philosopher who lived about 2,500 years ago. We know him primarily for the famous Pythagorean Theorem, which refers to a triangle that has a right angle at its base with sides of length A, B, and C. And the Pythagorean theorem tells us that this length squared, A squared, plus B squared is equal to the length of the hypotenuse, C squared. Now one might wonder, how would someone have proved this theorem 2,500 years ago? Well, we can't be sure what he did, but here's one way he might have gone about it. Here's that same triangle, which I've just tipped over so that it'll fit on the page nicely here as we proceed. And we can find the corresponding squares associated with each of the three sides, A, B, and C. And the areas here are A squared, B squared, and C squared. So an equivalent rephrasing of the Pythagorean theorem is that the area of A and the area of the square B is equal to the area of the square C. Well, that's interesting. Does it get us any further? Can we prove that indeed that's the case? Well, yes, we can. And what we'll do, notice these three squares are all built around that original triangle here. Now, the way we're going to proceed with this proof is by creating two squares that we build from this. And these two squares will be of equivalent size. And as you'll see, when we make the comparison of the two squares that we build, the Pythagorean theorem will fall out quite naturally and easily. So here's the first square. And as you can see, the length of each of the four sides of this square is A plus B. Furthermore, we can see that the area of this square is A plus B plus the area of four of those triangles. So I indicate that as 4t here. All right, that's one square. What about the next square? Well, here it is. This one's built around, instead of being built around A and B, this one is built around C. And we notice that this square also has the same dimensions on the outside, that each of the four sides of this square is the length A plus the length B. And it contains this square C plus four of the triangles. And so the area is C plus 4t. So that's nice. Now we pull these two squares of equivalent size back together, place them side by side. So again, the area of each square is the same as the other. And both squares contain four of these triangles. So let's wave our magic wand and just make those triangles disappear and see what we're left with. Well, what we're left with is the square A, the square B over here, and the square C over here. The four triangles have left, and so the area is no longer, the remaining area no longer contains the four triangles. So we've marked that out here. We've marked it out from this side as well. So we've dropped an equivalent amount from both of those squares, an equivalent area from both those squares. And what we're left with is an area here that equals a plus b and an area here that is equal to c. Well, that tells us that a plus b, that area is equal to the area of c. And that, as you'll recall, is simply a rephrasing of the Pythagorean theorem in the form that we normally see it: a squared plus b squared is equal to c squared. So, not bad, Pythagoras. Well done.